Welcome back. In this part, we're going to ask the question, in general, how close do the trapezoidal and Simpson's rule get to the actual areas under the curves? Well, it turns out that we can put bounds on the error between the estimated area and the actual area, which is given by the integral from a to b of f of x dx. So there are two inequalities down below. There's the trapezoidal rule inequality, which gives us a bound on the error between the estimated error using trapezoids and the actual area under the curve. And here by areas we mean net areas. So for this notation, the E is for error, the sub T means the trapezoidal rule, so this is the error using the trapezoidal rule. And the absolute values here are just making sure that it takes away any of the positive and negativeness of that could happen when you have the function go above or below the x-axis. So this is the absolute value of that error between the estimated area and the actual area, and we can put a bound on it. We can say that this is less than or equal to this m thing, which we'll talk about in a moment, times the interval width b minus a to the third power, all over 12 times n squared, where n is the number of subintervals. Now m, it says, is any upper bound on the absolute value of the second derivative of f on our interval from a to b. So that's what this m business is right here. And for Simpson's rule, it's very similar. We just have an s here for Simpsons, and the error bound is given by another m, where m is any upper bound of the absolute value of the fourth derivative on the interval from a to b. And here we have the interval length, b minus a, raised to the fifth power now for Simpson's rule, and then divided by 180 times n to the fourth power. So where did these things come from? Well, unfortunately, we're not going to be able to answer that here. These error-bound formulas are difficult to prove and are shown in numerical analysis type courses way down the road. However, we can at least get some intuition about them. For one thing, notice that the more and thinner trapezoids you use, the smaller the maximum error. So the bigger n gets here in this first error-bound formula, the bigger the bottom of the fraction is, and so the smaller the overall fraction will be, making the error smaller. So the difference between the estimated area using trapezoids and the actual area is going to get smaller the more trapezoids you use and the thinner they are. So also, given the value of n is given by this upper bound of the absolute value of the second derivative, remember what this second derivative means. It's a measure of how much a function curves, either concave up or concave down. It gives you a measure of concavity, but it tells you really how the function is curving. So if, like, for example, the absolute value of the second derivative is a large number, then the graph of f is going to be very curvy. It's going to kind of whip around really fast, making it harder for the trapezoids to fit the curve. Right? The trapezoids are only working with lines, and so if the graph is just whipping around and curving really quickly, the trapezoids are not going to be able to fit that kind of graph as easily. And in fact, if the second derivative of the absolute value of the second derivative is equal to 0, so we have no concavity, that would be the graph of a line, which is perfect for trapezoids to fit and gives us no error when using the trapezoidal method. If m becomes 0, then we have that the error between the estimated area and the actual area is less than or equal to 0. So we have no error, basically, in that case. Now, the error-bound formula is very similar for Simpson's rule, as we were just seeing, where you're using parabolas, remember, for Simpson's rule. But parabolas can match curviness better, and so if you want to put an error bound on this, you have to worry about farther derivatives, like the fourth derivative, before it's hard for the parabolas to keep up with the graph's curvature. Also notice that because of the n to the fourth in the denominator, Simpson's rule is going to have a smaller error over the long run. So for big values of n, the n to the fourth on the denominator is going to make the fraction a lot smaller than the n squared will. So Simpson's rule is going to have a smaller error when n gets larger. So that's just a general intuition about these error bounds. In example 3, we'll take a look at actually computing these error bounds. Moving on down to example 3 then, we're asked to estimate the error in the approximation from the integral from example 1, which used the trapezoidal rule. Well, what we're going to need is the second derivative to figure out this upper bound here of the second derivative. The b, the a, the n, we'll have all of that from example 1. It's just that we're going to need to get that second derivative, so let's get that. Well, to get the second derivative, we need the first derivative, and just as a reminder of what our function was from example 1, it's 1 over x. Peek back up here. So example 1, our function was 1 over x, and our a was 1, our b was 2, and n was 4. Let's come back down. So we need to get the second derivative. So here's the first derivative. What's the second derivative? If you said 2 over x cubed, that would be correct, because remember that this is like negative x to the negative 2. The negative 2 multiplies in front to give you positive 2, and then you subtract 1 to get x to the negative 3, which puts this down on the bottom as x to the third. All right, but now we're interested really in the second derivative, so the absolute value of the second derivative, which if we're thinking about our interval between 1 and 2, the absolute value bars are not really going to do anything here. You know, if our interval included negative x values, then we'd have to worry about the absolute value doing something, but since our interval is only from 1 to 2, those are the only x values that we're even considering here, that are in our universe, then the absolute value bars don't do anything. So now we got to figure out any upper bound on this absolute value of the second derivative. And here's where taking this function 2 over x cubed and thinking about the graph, and here I'm going to draw just like a quick little sketch of that graph down below. Thinking about the graph can help you figure this out. The graph of 2 over x cubed is going to kind of look like the graph of 1 over x. It's just going to fall as you go to the right. You'll have that asymptote at x equals 0, and then it's just going to fall as x gets bigger, because when x gets bigger, the fraction gets smaller. The main thing about this is that we're noticing that the function is decreasing as you go to the right. That's going to be the key part of this. So now let's write up what our interval is. It's from 1 to 2. And what our job is now is to find the maximum value of the absolute value of f double prime, of the second derivative of f, on that interval from 1 to 2. So we just have to figure out where is the value the biggest. So remember that what we've drawn here is we've drawn the absolute value of the second derivative of f. That's the graph we're looking at. So it looks like it's the biggest over to the left side of that interval. It's bigger over here. That's where it's the biggest, is at x equals 1. So what we can do is just take x equals 1, plug it into the absolute value of the second derivative, and we get 2 over 1 cubed, which is 2. So 2 is the biggest possible value of the absolute value of the second derivative of our function on the interval from x equals 1 to x equals 2. And so that is m. That's m. That's what m represents. It's the biggest possible value. It's an upper bound. Actually, it's any upper bound, so you could use m equals 3 if you wanted to. You could use m equals 100. But for these problems, we're going to be looking for the tightest upper bound, just so you know, just so I know that you know how to find these kinds of upper bounds. So you'll want to be able to take these steps instead of just writing down a Googleplex. We're trying to find the tightest upper bound. So then here we're going to take that m, put it into our error bound formula. So we can write now that the error using the trapezoidal method or rule is less than or equal to the m value we just found, 2, times b minus a, which is 2 minus 1 cubed, over 12 times n squared. 12 times 4 squared. Remember that n equals 4 in example 1. You have to plug in how many trapezoids you're using, and here we're using 4 trapezoids. Or in other words, how many subintervals you're chopping up your interval into. And we're chopping it up into 4 subintervals. Each subinterval, we're raising up a trapezoid. Okay, so when we compute all of that, we end up getting 1 over 96, which is the error estimate by using the trapezoidal method from example 1. So this is the maximum possible error, or a maximum possible error, in using the trapezoidal rule, using 4 trapezoids. So if we used 5 trapezoids, we would just increase the 4 to a 5, and that would be it. The m wouldn't change when we change the number of trapezoids. So the more trapezoids we use, the smaller this fraction is going to get, and we'll have less error between the area under the trapezoids and the actual area under the curve. Just for reference, this number is 0.010416 repeating. It's exactly equal to that. And so when we want to take something out of this, we can say that this will be correct to at least 1 decimal place. Because right here, there's nothing in the tenths place to really change the tenths place. The hundredths place could be changed, but not the tenths place. So the area under the curve approximation is going to be correct at least out to that decimal place. It'll be plus, or that whatever our trapezoid area is, plus or minus this error right here. Okay, so that's example 3. In example 4, we'll take a look at using the error bound for Simpson's rule. Thanks for watching, and see you in the next part.